And after that, I'll be discussing some of our recent research on algorithmic recourse and how counterfactual explanations can actually help with algorithmic recourse, and also about how feature attribution-based explanations can be helpful or not, as Mohammed said, with early detection of diseases and resume screening in the context of hiring, right? So essentially, we are going to probe this broader question of if and how can model understanding help in these kinds of real-world decision-making scenarios. Okay. With that said, I'm going to dive right into the first part, which is a brief overview on understanding machine learning models, right? I'm sure several of us are at this point aware that, several settings, like whether it is healthcare or whether it is finance or like loan approval, specifically in the context of banking and so on, or whether it is some of our favorite online applications such as, Facebook or Amazon or Goodreads and many other online portals and social networking sites, all of these are being powered by machine learning in some way, shape, or form, right? So banks are using these kinds of models to determine which applicants to give loans to. In healthcare also, there have been a lot of like this sort of risk detection style models that are being employed. And of course, online portals and, these kinds of like online social networking sites, they definitely employ a lot of machine learning today, right? So given that machine learning is present almost in the ubiquitous way around us today, I'm going to start with a hypothesis in this talk, and then hopefully as this talk unravels, you can see why I'm sort of making a claim like this. Model understanding can become absolutely critical, particularly in the kinds of domains like healthcare and finance, which involve lots of high stakes decisions, right? So that's where the power of model understanding can really come to the fore, and that can be really helpful. Okay, and we'll see throughout this talk instances of those, examples of those, and if that's actually happening, or is this something that we are just sort of assuming, and maybe we should not do that, right? So just to give a few instances or examples of how model understanding can even be helpful, I'm going to walk us through like a few quick examples just to give a sense of what exactly I even mean by model understanding and what are some use cases where it can be helpful, right? Again, at this point, we are talking a bit more hypothetically, and then this talk further shows more studies and results which sort of like test this claim in some sense, right? So for example, let's consider this scenario where there is a predictive model which is basically ingesting input images and making predictions about what animal is, in that image, right? So in this case, we see an example image of a Siberian husky. We are passing this through this predictive model, and the model labels it rightly as Siberian husky, right? So far, everything seems great. But if we look more closely and try to understand what features or what parts of the image the model is focusing on, then we realize that the model is actually looking at the snow in the image in order to make a determination about what animal is in the image, right? So in some sense, this model is kind of relying on this potentially spurious feature called snow in order to make this prediction, right? So what we have essentially built is not really an animal recognition tool or animal detector, but rather a snow detector, right? And, that could be fine in certain scenarios, but they may not be fine, or that may not be fine in certain scenarios. So the, researcher or the engineer who is developing this model might want to dig deeper to really understand what's going on and or potentially fix this so that the model is actually focusing on the features of the animal itself, like the face or its body and so on, when it is making this determination, right? So in this case, model understanding is actually facilitating debugging as we build these kinds of models, right? As researchers and engineers and practitioners build these kinds of models. Now let's think of a different scenario where there is a loan applicant and the loan applicant is submitting their application details to a bank, which is in turn employing a predictive model, and that model is throwing out predictions as to if the loan applicant's application should be accepted or denied, right? So now, if this is a pipeline that's sort of like in front of our eyes, and a loan officer is basically sitting at the end of this pipeline, if the loan officer is just told by the model that, oh, this loan is denied and that's it, like this applicant was denied a loan by the model, that's not as informative for either the loan officer or the loan applicant. In fact, if the loan officer is provided more details, for example, what is the top features that the model was looking at when making this prediction, that could be more helpful for them to determine whether they just want to go with the model's prediction or make their own decision, right? So for example, in this case, the important features are like race, salary, and gender, and race and gender being two of the features that you don't want to make loan decisions based on, right? So in this case, the loan officer might determine that, oh, this model has some, or rather this model is being biased when it's making this prediction. So maybe I'm going to make my own decision on this particular application, right? So in this case, model understanding is helping facilitate bias detection. In fact, if we look at the other side of the same scenario where there is the loan applicant who is dealing with this decision of a loan application being denied, instead of just telling that person that, oh, your loan has been denied and that's it, no other information, what would be helpful is to provide some kind of a means for recourse, right? So for example, instead of just telling somebody your loan has been denied, telling them that if you increase your salary by 50K or pay your credit card bill on time for the next 3 months, then please come back and apply and you're likely to get a loan. That is a lot more informative and meaningful to them, and in some sense will help them get a recourse, right? And in fact, this kind of focus on algorithmic recourse has been a prominent piece that has been highlighted in various acts and bills that are being passed all around the world, ranging from GDPR to the recent AI bill in the US, right? So in this case, model understanding is helping provide recourse to individuals who are adversely impacted by model predictions, okay? And of course, we can think of like other ways of model understanding. For example, if there is a model which is making certain kinds of predictions on patients, that is, it's tagging patients as healthy or sick, instead of showing those predictions to a doctor and letting the doctor figure out like, you know, which ones they would want to trust from the model versus which ones they may not want to, if we can actually provide some sort of understanding of what that model might be doing. In this case, we are giving a more global understanding of what the model is doing. For instance, for females, maybe the model is relying on ID numbers to sort of determine who is sick and who is healthy. In the case of males, the model is actually looking at like appropriate symptoms like cold, cough to determine if somebody is sick or not, right? So in that sense, you know, this global understanding of model behavior is immediately telling the doctor that, oh, while the model seemed to be doing fine, it's looking at relevant features in the case of male patients. The same is not true in case of female patients, so I should not trust its predictions for that group, right? So in this case, model understanding is helping the doctor determine if and when to trust model's predictions when making decisions. Okay. And similarly, this kind of information can also be very helpful to regulatory authorities who are determining if models sort of need to be deployed at a wider scale, or if models are ready to be deployed at a wider scale, right? And if an authority sees that, in fact, this is what the model is doing and it's using irrelevant features for about half the population, that's the female population, then they may not, then they may deem that this model is not ready for deployment, right? So in this case, it's allowing us to vet models to determine if they're really suitable for deployment in real world. Okay. So clearly there is a lot of utility for understanding what models might be doing when they're making either individual predictions or, you know, just their overall global behavior as a whole, right? So the utility ranges from debugging to bias detection to recourse to determining if and when to trust model predictions and vetting models to assess suitability for deployment. And there are several stakeholders who can benefit from model understanding. This could include end users ranging from loan applicants to patients or decision makers such as doctors, lawyers, judges, regulatory agencies, as well as researchers and engineers who are developing these models, right? So there's a wide set of stakeholders that can actually benefit from understanding models. Okay, so now that hopefully we have talk through some of these scenarios, and hopefully we can appreciate that model understanding can in fact be useful in certain contexts, what are some strategies to even achieve them, right? The first strategy that has been sort of traditionally employed in machine learning literature is to build models that are inherently interpretable. So for example, linear models like logistic regression, linear regression, shallow decision trees, simple rule-based models having like if-then or if-else-if rules. So these are all the kinds of models that are considered inherently interpretable because we can look at them and really understand how the prediction is being made, right? So developing such models is one way to achieve model understanding by default, right? Another way to think about model understanding, and which has become more popular in the last 5 years or so, is explaining pre-built models in a post hoc fashion. So for example, we could have these complex black boxes, or we could have these like super huge models such as deep neural nets with like several hundreds and thousands and these days millions and billions of intermediate layers. So we could take such models and then pass them through some sort of explainer algorithms, which in turn break down these models into combinations of simpler models, such as linear models or shallow decision trees or like rule sets and so on. And that is again human understandable or human interpretable, right? So two strategies: either build models that are inherently interpretable or explain complex pre-built models in a post hoc manner using simpler constructs that we can understand, right? So when to do which one, right? So when to go with what strategy, or when to rely on inherently interpretable models versus post hoc explanations is often a common question that emerges as we are having this discussion, right? And in fact, even the question of do we even need post hoc explanations, like why don't we just go with inherently interpretable models, right? And the answer to all of those questions lies in some of these plots, okay? So typically, while models such as linear regression or shallow decision trees and so on are interpretable, are understandable to human users and users, they are turning out to be not as accurate as more complex models. For example, ensemble models like random forests, which comprise of hundreds and thousands of trees, or deep neural networks, which are very complex nonlinear combinations of several different kinds of variables, right? So these complex models are turning out to be more accurate than the simpler models, especially when your data is high dimensional and also when your data sets are huge, right? So given that reason, given this tension between the trade-offs of the interpretability and accuracy, post hoc explanations have come about as some sort of a mediating solution that can bridge this gap, right? So in some sense, because these trade-offs exist, and there may be settings where we may not want to sacrifice accuracy for the sake of interpretability. That's why people have resorted or started using, building models as complexly as they want, as accurately as they want them to be, and then using these post hoc explanation methods to sort of explain the predictions of these models or the behavior of these models so that users can understand them, right? And just to give a simple intuition of when might an inherently interpretable model be accurate enough, and we don't even need to resort to post hoc explanations, we can consider the simple example of a two-dimensional data set, right? And the red is basically a negative class, and then the blue is a positive class. So as we can see, the data here is almost linearly separable. So I can draw like a line and then separate the two classes here, almost separate the two classes here, right? So in this case, simpler models such as a linear regression or a logistic regression can actually work because the data is easy to separate, right? So the two classes in the data are easier to separate. So in this case, we can build an inherently interpretable model that will also be very accurate, right? But if your data looks something like this, if the separation between your two classes, this red and blue, is the boundaries are highly nonlinear, in that case, we may not be able able to use very simple models to sort of accurately capture these boundaries between the two classes, in which case we are stuck with this interpretability accuracy trade-offs. So complex models are likely to achieve higher accuracy, and therefore if you don't want to sacrifice accuracy for the sake of interpretability, you can build a complex model and then use a post hoc method to sort of explain the predictions of these models, right? And beyond these kinds of trade-offs, sometimes you just don't have enough data to build your model from scratch, and all you have is you're dealing with some sort of a proprietary black box that somebody else has handed over to you. Like another company has built a model, they're not sharing their proprietary secrets of the model, they just give you query access where you can give a data point to the model and it spits out a prediction, and that's all you have to deal with. Even in that case, post hoc explanations can be very useful, right? So essentially, just to summarize our discussion, if you can build an inherently interpretable model, which is also adequately accurate for your setting, that might be the way to go. Otherwise, post hoc explanations come to the rescue, right? The reason why we are even thinking about this is that since post hoc explanation methods, as we'll talk later in the talk as well, are essentially approximations of the underlying model behavior, just like any approximation, there may be some errors that may creep in, right? So if we want to avoid that, the best way is if you can get a model that's straight up inherently interpretable, also adequately accurate, we should just do that. Otherwise, post hoc explanations can come to our rescue, right? And the rest of this talk will mainly focus on post hoc explanation methods and their outputs, and what is good and bad about them, and if they're really useful for real world decision making. Okay. So let's think a little bit about what exactly is an explanation before we dive into these outputs of post hoc explanation methods, right? So an explanation more broadly is just an interpretable description of model behavior, right? So there is a classifier which we want to explain to an end user, right? So that's basically our two sets of entities that we are trying to cater to. And explanation is sort of this bridge between the two. So explanation needs to be faithful to the underlying classifier or the model that it is trying to explain, and it should also be understandable to the end user who is at the receiving end of it, right? So there are two properties that need to be balanced simultaneously. One is faithfulness with respect to the underlying classifier, and the other is interpretability with respect to an end user who is going to use this explanation. So those are the two sort of criteria that we would care about, right? And there are different ways of thinking about explanation depending on who the end users are. For example, if your end user is probably the engineer or the researcher who developed this model, maybe sending all the model parameter theta may work, right? But the same will not work if your end user is, let's say, a doctor or a judge who may not have as depth of an understanding of these model parameters associated with these machine learning models. Another way to think about explanations is send many example predictions. You sort of show different examples and the predictions that the model is making, and then the user sort of figures out a pattern, right? Or you summarize the behavior of the model, at least in different pockets of the feature space or the data, using a rule or a tree or a program and so on, and that could also constitute an explanation. Or we could just select the most important features or data instances, and those could serve as explanations. Or we could describe what somebody needs to do to a data point in order to flip the model prediction. That could also be considered an explanation, and so on, right? So, and these are all the different categories of post hoc explanations for which different techniques to construct these have come about in the last 5 to 6 years. Okay. At a very high level, post hoc explanations have been categorized into two classes: local explanations and global explanations. So local explanations, as the name suggests, means that we are thinking about the description of the model behavior in a very small target neighborhood. So essentially, local explanations are geared towards explaining why a model is making one prediction, an individual prediction, right? Global explanations, again, as the name suggests, is an interpretable description of complete model behavior. So in some sense, you get a bird's eye view of the model behavior, but that may not be as accurate in some sense, right? So because you're trying to explain a very complex model using like simpler interpretable descriptions. So essentially, you're giving a bird's eye view of this complex model behavior, whereas local explanation, you're just trying to explain individual predictions or the rationales behind individual predictions that are being used by the model, right? And a lot of this talk will be focusing on local post hoc explanations, since that's a predominant category of post hoc explanations, where there has been a lot of work from other groups as well as our group in the past few years, right? Okay, so with that, we're pretty much done with the overview of like just giving a big picture idea of what it means to understand machine learning models. Now we are going to jump into some of the core pieces of research that I wanted to discuss today. So if there are any questions at this point, I can pause and take one or two, or I can keep going into the next part of the talk. Okay, I think I can keep going. All right. Okay, so let's start with the first subpart of our second part of the talk, which is counterfactual explanations for algorithmic errors, right? So what do I mean by this is essentially we are talking about this scenario. So we are looping back to the example that we started with at some point in our motivation. So where there's an applicant who sent a loan application to the bank, which is employing a predictive model, which is determining if the applicant's application should be approved or not, right? And in this particular case, the application was denied, unfortunately. So instead of just telling the applicant that your application was denied, one way to deal with this scenario is sort of the predictive model can work with this recourse finding algorithm in order to produce a suitable recourse that can be useful to the applicant. For example, right, increase your salary by 50K and pay your credit card bills on time for next 3 months in order for you to get a loan, right? So that you can reapply and then your loan gets approved. So essentially, that kind of recourse can be very helpful to users who are receiving adverse outcomes, but that's exactly what is also done by this sub area of post hoc explanations called counterfactual explanations, right? So a counterfactual explanation essentially tells us what feature values should be changed in order to flip the model prediction. For example, increase your salary by 50K or pay your credit card bills on time for next 3 months, right? So that is exactly the description that counterfactual explanations provide us, and therefore they are considered good candidates for providing algorithmic recourse, right? At a very broad level, the intuition behind generating this algorithmic recourse or counterfactual explanations, by the way, given that these terms are essentially referring to the same thing, they are often used interchangeably both in papers and in talks. So whenever I say algorithmic recourse, that also refers to counterfactual explanations and vice versa, right? The idea behind generating such algorithmic recourse or counterfactual explanations is the following, right? So at a very broad level. So you essentially have a point X here, which is on the negative side of the decision boundary of the model. And you want to find the point that is closest to X, but on the positive side of the decision boundary. So that's one way to think about it, right? So essentially, there is X, which is now getting negatively classified. We want to find a counterpart of X, which is on the positive side of the decision boundary, so that it can just evoke a positive outcome from the model, right? Now, there are different ways to sort of find a point on the other side of the decision boundary corresponding to X, right? So because X can be sort of transformed into the CF2, which will also get a positive outcome, or X can be transformed into CF1, which will also get a positive outcome, right? So both are valid ways to get a positive outcome, for X. If we change X to those, you will get a positive outcome, or you'll receive a positive outcome. right? So there are several algorithms which sort of do this, and the proposed solutions essentially differ on how to choose among candidate counterfactuals. So if CF1 and CF2 are both valid ways of changing X to something else so that you get a positive outcome, which one to pick? Should I pick CF1 or should I pick CF2? And maybe you pick CF1 because it's more closer in terms of some kind of L1 or L2 distance, or you could pick CF2 because it may be lying on the data manifold, or it may be closer to a more realistic data point than CF1, right? So there are different strategies that different algorithms employ. And also these algorithms differ based on how much access is needed to the underlying predictive model, which means does this recourse finding algorithm need to see all the model parameters, or can it assume that the underlying model is a black box and all it needs is a prediction output by this model? So there is a huge spectrum in between, and how much of model access is needed is another criterion that sort of distinguishes different algorithms that exist as of today, right? As I just mentioned, one strategy to do this is minimum distance counterfactuals, which is find a counterfactual that flips the prediction. So counterfactual is essentially another instance or a counterpart of the original instance X, which flips the prediction and is also closest to the original instance. So find something that is closest in terms of L1 or L2 distance to the original point we started with. Another strategy is feasible counterfactuals. So again, find counterfactuals that actually involve feasible changes. For example, if some counterfactual is involving a change to race or gender, that is not a valid counterfactual because those changes cannot actually be made easily by humans, right? So considering feasible counterfactuals or causally feasible counterfactuals, which means we have an underlying structural causal model, and we only consider those counterfactuals as permissible, which satisfy this causal model of the underlying data, right? So for example, we should not say something like somebody should increase their education without saying that they'll also increase their age, right? So that causal relationship between the two features should be respected when generating counterfactuals. So there are different strategies for sort of thinking about how to generate these recourses or counterfactuals or counterfactual explanations in this case, right? So some of our recent work was about understanding how useful are counterfactual explanations to loan applicants, right? So we did a survey with about 182 bank customers who have applied for loans over the past year, and 56% of them have successfully obtained loans, and remaining were either denied loans or they were asked very high interest rates, which they could not afford, so they did not take a loan, right? So we conducted an online survey asking these applicants about utility and helpfulness of these kinds of counterfactual explanations prescribed as recourse. And some of the survey questions were, how helpful is a recourse prescribed in the form of this kind of a counterfactual explanation? And there is this kind of a scale where they can rank the helpfulness or utility of the recourse, right? And would such a recourse motivate you to change your circumstance and reapply for loan with the same bank? Again, we have this sort of a Likert scale with different values ranging from strongly agree to strongly disagree. And how would you feel if you implement the recourse and the bank still denies you the loan? Would you still do business with the same bank if this happens, right? And would you expect the bank to give you a loan even if you fall slightly short of the presented or prescribed recourse? Okay, so these are some of the survey questions. We also asked them a lot more, and the answers to these questions are not only interesting, but they've also motivated some of our other methodological research that I'm going to briefly talk about, right? So a majority of 93.4% of total participants said that a counterfactual explanation prescribed as a recourse would be extremely helpful or very helpful. And about 76% of total participants agreed or strongly agreed that a recourse would motivate them to act on it. And this was basically including about 81.2% of unsuccessful applicants, and 97.8% of total participants said that they would be very dissatisfied dissatisfied if the bank denies a loan after they implement a recourse. And in fact, a majority of 82.9% of these participants said that they would never do business with the same bank again if they ever did that to them, right? And 95.1% of these participants agreed or strongly agreed that the bank should give them a loan even if they fall slightly short of the prescribed recourse. So for example, if they were asked to increase their salary by 5K, and if they did so by like 4,950 or something, so they are still expecting that the bank would give them a loan, right? So because they got pretty close to the prescribed recourse in some sense. So one of the things that stands out here is that once a bank is going to employ recourses and prescribe them to people, they would be pretty dissatisfied if for some reason their loan still gets denied after they implement the course. And that can cost the bank their customers, that can cause a lot of customer dissatisfaction to the bank, right? So now this is a problem that we try to dive a bit deeper into to understand why this could happen, at least what could be some of the technical modeling and machine learning related reasons where this could happen, and how to think about them or how to think about fixing them, right? So one of the challenges with these existing recourse algorithms is that recourse that is generated is typically not valid when the underlying model even changes slightly, right? So the recourse that you will get prescribed is valid for the model that is basically like available today in the bank. But even if that model gets like slightly changed or slightly tuned or their hyperparameters tweaked, and there are some changes, there's no longer any guarantee that, all the prescribed recourses so far will hold at all, right? But the truth is that models are often regularly updated in practice because there's often like changes in the data set shifts, which involve, or rather which call for retraining of these models, right? Sometimes even audits of the models may lead to changes in the models so that the models are more fair or they're more robust and so on. But like the reality is models often get updated in practice in banks, financial institutions, and pretty much everywhere else, right? So how to then think about this problem or rethink this problem of ensuring that the recourses that we are providing to somebody today will still remain valid, say about few months from now, despite any changes in the underlying model. So that was one of the works that we did, very recently at Murex, right? So essentially, there are two pieces here to how to go about this problem or how to solve this problem, or at least the approach that we took. So first is we need to characterize or understand what kinds of shifts can happen in the model, right? So for example, if we think of it as, let's say just for the sake of understanding, we are thinking about linear models. So we have linear regression and logistic regression type models. So their weights are the parameters of those models, right? And then we can consider or characterize shifts in this model as some sort of additive increments or decrements to the model weights, right? So we are essentially like kind of shifting the model weights by adding some delta, subtracting some delta. So in that sense, you can capture possible model shifts to a given linear model by considering additive shifts or additive changes to those weights, right? So that's one way to think about it. Similarly, such additive shifts can also characterize changes in more complex models. For example, if you have a deep neural net and it has a bunch of parameters, you could still think of changes to the model as some sort of like shifts to these additive shifts to these model parameters, right? So that's how we thought about, or we're characterizing shifts in this work. And once we have characterized model shifts or how they could look like or how they could happen, then the next question is essentially how to generate a recourse that is robust to such model shifts. Okay, so the idea here is that normally a typical sort of the loss function for finding a recourse would essentially try to do the following. You sort of try to minimize the find a counterfactual x prime given an original instance X, such that the distance between X and X prime is small, but also the model's prediction on X prime is 1, right? So that's the classic loss function. But with this kind of a new way of generating recourse, which needs to be valid across different kinds of model shifts, we are now considering the sort of worst case recourse loss under the possible set of shifts that we are characterizing, and we want to minimize that, right? So in some sense, you not only want to find a point X prime that is close to the original instance X and which flips the prediction of one model, but you want to maximize the chance that this instance X prime you're trying to find also flips the predictions of multiple models within your set of plausible model shifts, right? So that's the objective. So essentially, the structure of this objective essentially can be formulated as a min-max optimization problem. And, again, there are connections to between this and the literature on adversarial machine learning, where they commonly use min-max optimization problems and then use adversarial training to sort of optimize such functions, right? Such optimization problems. And we also theoretically demonstrated the goodness of this proposed approach, and the recourses that were generated by this approach were essentially valid, or at least the goal was to make them valid across multiple possible changes in the model. Right. We carried out a bunch of experiments with some data sets which capture correction shift, temporal shift, geospatial shifts in the data. So there was essentially data from 1 year, but then there was also data from the following year. And then we had these kinds of shifted data sets with which we trained 2 different models. So we were essentially capturing how retrained models because of shifted data would look like. So that's why we considered some real world data sets. And essentially what we found was that the recourses generated by our framework were on an average 73.82% more likely to hold across model shifts compared to those output by baselines, which can potentially help with some of these issues that we talked about, where at least people who implement the recourse will not be denied a loan once they come back, right? Because the model has changed, right? At least those kinds of technical reasons, right? So essentially, the recourse generated by our framework ROAR are valid even when the underlying model is updated, and that can be pretty useful, right? So essentially, we are trying to avoid the scenario here where somebody takes the recourse from the bank and the model today, and then they go back and work very hard on implementing this recourse. And in the meanwhile, the bank has updated the model, and this person implements the recourse and comes back after 6 months and says, oh, look, I've implemented my recourse, but by then the bank's model has changed, which means that recourse that this person was given 6 months back is no longer valid. And therefore, the bank is like, sorry, our model has changed and we can't give you a loan anymore. So we are basically trying to avoid that scenario with all this framework by producing recourses that are valid across possible shifts in the model. Okay. All right. So there was another striking finding from this survey that we did, which was that about 95.1% of participants agreed or strongly agreed that the bank should give them a loan even if they fall slightly short of the prescribed recourse, right? So which essentially means, again, this is not something that existing recourse algorithms actually account for. So currently the expectation is that you almost do some sort of a precision landing. So if you're asked to change your salary by 5K, you have to exactly change your salary by 5K for you to get a positive outcome or prediction from the model, right? But we developed another algorithm recently, which basically relaxes this condition. Again, it's a min-max style optimization formulation, and then we used adversarial training to solve that formulation. But essentially, the idea is that even if you don't just have to land exactly at the prescribed value of the recourse, but even if you are off by some epsilon of that, you will still be able to evoke a positive outcome. So prescribing or even constructing or generating such recourses, that was some of our recent work, which is currently under review. Okay. So next, I'm going to talk about a slightly different class of explanations and a bunch of user studies that we did with recruiters and doctors in order to see how helpful those explanations even are to such audiences, such end users. Okay. So before we get into that, I just want to give a quick glimpse into the conceptual understanding of what this feature attribution based explanation is and what's like one intuitive way that these are generated even today. And then I'm going to talk about the user studies and the results, right? So essentially, the idea behind a lot of these local post hoc explanations, or why they are becoming more and more popular, is that while a complex model at a global level can have very complex nonlinear decision surfaces which are hard to explain or understand. If you sort of zoom in into smaller pockets of the feature space, they actually behave like linear models, right? So that's essentially like one of the key underlying intuition that has informed the design of a lot of local post hoc explanation methods, right? So essentially, at a global level, you might see this kind of a nonlinear complex function, but like if you zoom in enough, for example, if I zoom in close to this point, then I see that even this complex nonlinear model is behaving like a linear model where it's essentially like we are drawing a line, we are fitting a piecewise linear function there, and that's separating the two classes, right? So that intuition is what is exploited by this class of explanations called feature attribution explanations, which are also local post hoc explanations. They focus on explaining individual predictions, right? And one such very popular algorithm in this category is called LINE, which stands for locally interpretable model explanations. The idea behind LINE is the following. Okay, so let's say you want to explain the prediction of this particular point xi by the underlying model, okay, which is a complex model, potentially a black box as well. We don't see anything internal. We just see the predictions of this model, okay? The way to sort of explain the prediction of this particular instance according to LIME is as follows, right? So first, essentially take the point and then sample points around X. So the points in the local neighborhood of X in some sense, right? And then once you so essentially take a point X, perturb it slightly and basically get samples around X and use the underlying complex models to label these points around X, okay? And then weight these samples according to the distance to xi, which means points that are closer to this xi get higher weightage, and points that are slightly farther away from xi get like lower weightage. And then, you basically learn like a linear model, like a linear regression model on these weighted samples, right? So you're essentially learning a weighted regression model to sort of fit the predictions of the underlying complex model in this small neighborhood around X. That's what you are doing, right? And once you basically have that local linear model for this point that you have just fitted as the way I described, then you can just use that to explain how the model is making that prediction, right? So in some sense, you have weights associated with each of the features, and they'll tell you how important each feature is, just like we look at weights of a typical linear regression or logistic regression model and understand the importance of different features in a particular prediction. Now, the same way we can do this and sort of understand what are the important features to this prediction, right? So that's the simple idea. So essentially, instead of like looking at this whole complex model and like being overwhelmed by its complexity, what we want to do is take a point, perturb it a bit, generate a bunch of points around it, use the underlying model to label these points, and then essentially fit a local linear model to sort of, mimic the predictions of the underlying model on these points that we have sampled, right? And then essentially you have used a local linear model to sort of mimic the underlying model just in that small neighborhood or vicinity. That's what you're doing, right? Okay, so that means essentially the output of methods like LIME and other feature attribution methods is they'll assign weights to each of the features, and we can actually determine what are the important features by that, right? So for example, I can say what the top K features are corresponding to a given prediction of a particular underlying model or a complex black box model, okay? So the first user study that we did was basically to understand if these explanations are any useful. More specifically, we wanted to understand if we can improve the accuracy of decisions in the real world using these kinds of feature attribution based explanations, right? So the prediction problem that we considered is that, is a given patient likely to be diagnosed with breast cancer within the next 2 years? Note that this is not a diagnosis problem, because one thing we know is that doctors are pretty darn good at diagnosis, and they're also pretty great at like treatment recommendations. What we were trying to look at is the sort of forecasting the risk of somebody getting a serious disease within the next 2 years. Right. So we carried out user studies with about 78 doctors who are residents in internal medicine across Harvard and Stanford Medical School. And the task was that each doctor looks at 10 patient records from historical data and makes a prediction on each of them as to whether this patient is likely to be diagnosed with breast cancer within the next couple of years, right? And a lot of variables such as the patient's current symptoms, current disease diagnosis, family health history, their blood test results, and as well as their metabolic panel results were all part of the input data of the patient record provided to each doctor. Okay, so we basically split the doctors into 3 different buckets. So bucket 1 corresponds to the condition where the doctor is just looking at this patient record and then making a decision about whether they're likely to be diagnosed with breast cancer in the next couple of years. And what we saw was that the doctors were right about such a prediction with an accuracy of about 78.32%. Then there was the second bucket, or the second condition, where the doctor did not just have his own expertise or her own expertise to rely on, but they also had access to the prediction of the machine learning model for each patient. So for example, at risk is the label given by the model, as well as the probability with which the patient is deemed at risk. So in this case, the model is saying that there is a 0.91 probability that the current patient is at risk, right? So the doctor had the prediction of the model and the probability associated with that prediction with them. And the model itself had an accuracy of 88.92%. So just the model itself was actually more accurate than the doctors themselves standalone. But the combined accuracy of the doctors plus the model prediction with the probability actually turned out to be 82%, which was lower than what the model standalone accuracy was. Our follow-up interviews reveal that doctors kind of either weaned on the side of either over trusting models at times and then just agreeing with the model, even though the model was not very confident, or the model was confident but was just wrong. Or there were doctors who kind of weaned to the other side of, oh, I'm just going to make my own decision, I'm not going to trust it. And in which case we seem to have lost the power of it did increase a bit. The accuracy went up from 78.32 to 82.02, but it's still lower than the model alone accuracy, right? So we considered the third condition where there were doctors also had access to the model prediction, associated probability, but in addition, we also added these explanations in the form of the top 4 important features according to the methods that I just described earlier, such as line. And we showed those top 4 features that the model is relying on to make this prediction to the doctors. And in this case, the combined accuracy turned out to be much higher than any of the other accuracies we have looked at so far, which is 93.11%. So in some sense, this experiment made us see that doctors are able to better appreciate the model and what it is doing when there is more information about what features the model is relying on. And that kind of, in this scenario at least, it helped them like better assimilate that along with their judgment and then make a call in an appropriate way, right? So for example, there were some instances where in this case the features were relevant. There were some instances where the features were turning out to be something like this, which is appointment date, appointment time, zip code, and so on. And in those cases, the doctors had a reason to say, oh, even if the model seems to have a high confident prediction, the features that it is relying on are like completely irrelevant ones. So I'm just going to go ahead and make my own decision in this case, right? So the explanations really help them tease out when to trust the model predictions and when not to. Okay. And in a similar vein, we actually wanted to explore another question, which is, can we reduce biases in decisions in the real world using, feature attribution based explanations like the ones we just saw, and also fair machine learning models, right? In order to sort of answer this question, we carried out this task where we were thinking about a scenario of screening resumes for hiring. So basically, a recruiter is debating about this question of, should a given candidate be considered for an interview for a software engineering position? So that's the question they need to think about as they look at a resume that they have in front of them, right? So we carried out this user study with 92 recruiters, and each recruiter looks at 10 resumes and makes a decision for each candidate independently. So there is no cap on the number of slots or anything. They can say yes to as many as they want. Essentially, that decision will be made independently for each resume. So in order to carry out the study, what we did was we basically took a bunch of resumes from some of our partner organizations that they had, and we took a resume and then put a US common female name to the resume, and also created an identical copy but with a US common male name, right? So same resume, we had a female name, we had a male name, all US common names. And given that, the probability of the selection should be the same for males and females when a human looks at such resumes, right? So because they're essentially identical, we have just like flipped or switched names. And we also made sure that the algorithms that we were training in order to make a prediction about which candidate is likely to succeed at this job, because that's the way recruiters think when they're screening resumes, as, is this candidate going to be a good fit, and will they do well if we send them to the next stage of interviews, they get interviewed, get a job, will they be a good employee, will they suit this role, right? Like, will they have good performance, say 1 year from now? So those were the outcome or the ground truth labels that we considered, and we trained a model on that kind of data. And then essentially we also ensured that the model itself was not looking at any gender related attributes, because we scrubbed all the names and other aspects there, and made it like completely free of any gender related information. And we also ensured put constraints on our algorithms models itself, that they should be fair, and their selection probability for both male and female genders should be the same. Okay. Again, we considered 3 different conditions. So the first condition was recruiter only, where a recruiter is looking at this resume and making a decision of if they should pass this resume on to further interview or not, right? So what we are measuring now is not accuracy, but rather gap in selection probability, which is the probability of being selected if you are a male minus the probability of being selected if you are a female. So essentially, that's the gap that we are looking at here. Right. So the gap actually turned out to be pretty big with the set of recruiters. Of course, we have been sort of continuing this experiment, and the gap numbers are slightly different at this point, but the gap turned out to be still pretty huge when just humans are making this decision, indicating a clear bias towards one gender, right? And then the second condition that we looked at was, of course, recruiters, and they have access to the prediction of the model, and they also have access to the probability of this prediction, okay? And this combined set of decision-making had a gap in selection probability of about 0.288. So this is slightly lower than 0.32. Not significantly lower, but slightly lower. But one thing to note is that the model's gap in selection probability itself is super small. This is like 0.01 compared to 0.288 or 0.322. So the model itself is doing a great job in terms of not having a gap in selection probability. But clearly the recruiters, when they do the job individually, or even in conjunction with model predictions and their probability, essentially their gaps in selection probabilities are higher, right? Now, the third condition is we don't just show the recruiter the model prediction and the probability, but we also include the important features, again, output by these explanation algorithms that we were talking about throughout. So for example, in this case, the recruiter sees that the features that the model was relying on when suggesting that a particular candidate should be interviewed are GPA and GPA in computer science and internships and number of GitHub repos and so on. And that, in fact, that combined decision-making process resulted in a gap in selection probability that was much, much lower, which was 0.05, right? Of course, the models still seem to have a smaller gap in selection probability, but that's because we have heavily optimized the model for that. But essentially, the gap in selection probability for the human users has drastically reduced from 0.32 to 0.05, right? So that's a significant jump in terms of the gap in the selection probability, right? And which means essentially the answer is explanations are somehow, serving as a way for us to reduce biases in real world decisions as well, right? When we did a lot of post interviews with these recruiters as to, why they made the decisions they made, why did they flip their decisions once they saw explanations and so on, in some sense, what we realized was something very interesting, that this kind of showing the important features that the model was using almost served as a behavioral nudge for them. So in some sense, the recruiters felt like the algorithm's top features were sort of pointing them to certain things they were ignoring, especially for things like, number of stars on the GitHub repo or number of GitHub repos for female candidates were often being discounted when recruiters were just doing this on their own. But the models were relying heavily on those attributes when they were saying, oh, this female candidate should be interviewed, right? In some sense, like it was acting these sort of, the important features that the model was using were serving as behavioral nudges to these recruiters as they were making their decisions. In fact, one person quoted that essentially they felt like it was another person out there who was making a similar decision, but was using some critical features that they missed, and they actually changed their mind about, recommending a candidate for interview. So that was a pretty interesting insight. Okay. So with that, we are pretty much at the end of this talk. I'm just going to conclude with some summary points, and happy to take if there are any more questions towards the end. But essentially, model understanding has actually re-emerged as one of the most sought after topics in machine learning in recent years. It was a sort of a topic, like I think a while back, and then the focus sort of went on to developing more complex models. But now this has become this has yet again become an important topic in machine learning research. If done right, model understanding can be very helpful in probing deeper into model behavior beyond predictions and confidences. It's also important to pay special attention to quantifying the correctness or accuracy of model explanations. Otherwise, again, we might end up trusting and deploying models with undesirable biases, right? So we need to, of course, pay attention to the accuracy of the models and their predictions. But when we are looking at or relying on explanations, we also need to pay attention to the correctness or accuracy of the explanations themselves, right? That's another key aspect. And it's still a nascent field with a lots of scope for for new research in terms of understanding utility and improving reliability of existing methods. So essentially, there is a lot more to do, both in terms of like how useful they can be for decision making in different real world applications, or even how to just design better methods that can result in or generate more accurate explanations that are a lot more faithful to the underlying models. With that, I'm going to break here and thank you all for your time and attention. Thanks.
Thank you so much, Hima. That was a very interesting kind of journey, not only through kind of the fundamentals, but also some real world impact. If we have any questions, please feel free to put them into the chat or raise your hand, and we'll just go in order.
I do see one question from David, but I think it was just put from me probably. Is there room or scope in your work and model of recourse modeling that would improve like short timetable? I think autonomous cars, military decision making on battlefield, etc. Actually, that's a very interesting question, because this kind of recourse, as in, what else you could do to change your prediction, that is something that does have some implications with respect to the autonomous vehicles. So, for example, we have been in discussions with some autonomous car companies, which I'm not allowed to name, but essentially, we have been in discussion with them to sort of like see how these kinds of, because whenever there is, an unfathomed incident or an unanticipated incident, like, for example, a car crash, people often want to know why this autonomous vehicle did what it did and ended up in that situation, right? So in those contexts, thinking about what change could have made this autonomous vehicles algorithm sort of do the right thing is actually one of the key things that they're interested in looking at, because that will help them understand, oh, with this it's not working, but the model thinks that if if the scene in front of me, or if the view in front of the car was slightly different, then it would have, probably just driven straight, which it should have done, and now it has taken a left and it has hit something, right? So I think there is definitely a lot of scope for including these kinds of, whether it's recourses or more broadly explanations in the context of autonomous vehicles, for sure. Thank you. Thanks for the question.
I think we have a question from Robin as well. Go ahead, Robin.
Hi, I was wondering if there's any discussion about some potential risk because of the explainable model. For example, in an individual perspective, if you want a loan, it is good to know how the model works so that you can modify, you can start paying your bills on time. But in an aggregate sense, there could be a risk where people may exploit it. For example, think of a situation where you may use this for college admissions, and somehow people got to know that in this algorithm, some very specific extracurricular activity is the way to go. And then everyone's going to start to do the extracurricular activity, which obviously isn't the way that the college wanted, especially in terms of diversity and in terms of, this integrative assessment that they're supposed to make.
Yeah, great question. And I think you're absolutely right that one of the downsides of the sort of transparency or explanations, whether it's recourse or something else, is that you're exposing more information about the underlying data, because essentially you're explaining what the model is doing, right? And the model is doing what is captured in the data pretty much, right? So in some sense, there is a risk that first of all, you might leak some of the privacy aspects of the data, like who is in the training data and so on. Second of all, as you said, there could also be these kinds of adversarial attacks where people can look at the recourse and start gaming the systems. While there needs to be more work and thought put into that, and you're right that it's a very important thing to consider, I just want to add one thing. So I briefly discussed somewhere through the middle of my talk, where we talked about using these kinds of like structural causal models to generate recourses, right? So the idea of doing that is to actually avoid any kind of spurious variables from being acted upon. So in some sense, for example, as you rightly said, if people realize that, yeah, like if I put this one extracurricular activity, there is something that's happening in the algorithm and I'm just getting admitted, right? But once you use the structural causal model, you are essentially going to get rid of such spurious correlates, because that extracurricular activity might itself not have anything to do with the success outcome, but maybe that extracurricular activity is actually associated with some other thing, right? So which is actually impacting the outcome. So we actually saw the scenario even in like, for example, the bank situation, where somebody's salary and economic status directly impacts their ability to repay a loan. But that also correlates with the kind of phone they carry. For example, iPhone versus like landline and so on, right? So there is a risk that if these algorithms are not sort of developed properly, it may say that, oh, if this person has iPhone, like just give them a loan, right? But the truth is that's happening because that iPhone is correlating with this feature, which is somebody's salary and economic status. That has a direct bearing on the outcome of whether somebody pays a loan, right? So, but the causal model will prevent us from using these spurious correlates when prescribing recourses. That's one way to sort of, navigate this issue and not enter this in the first place. But you're right that that's an absolutely critical point to keep in mind, and more work is needed on that to avoid these kinds of issues, catch these kinds of adversarial attacks.
This is very helpful. Thank you.